Thank you very much. Thank you. So thanks a lot for inviting me to speak and for organizing this very nice event in this very beautiful place. So I haven't worked on topics related with modular forms for the last few years. And also, I don't know much about resurgence. So I decided to give a little bit of a philosophical talk on what I currently know about the relations between modularity and monodromy. By monodromy, I mean multivaluedness of functions related to being solutions of differential equations. So here I wrote down a little bit of notation. It's everything is quite standard except for the definition of the Eisenstein series, the holomorphic Eisenstein series. For people, more arithmetic people, this is also quite standard, but I think usually in this conference, Eisenstein series are defined as this kind of lattice sums. I want to normalize them in such a way that the coefficients are rational numbers. So this is the Bernoulli numbers. And that's why I added this little bar here. Okay, good. So the starting point of this talk is the fact that you have all noticed in various times, also in this conference, that there is this kind of duality between objects which are holomorphic but non-modular, and objects which are modular but not holomorphic. So I'm gonna be a little bit vague on what I mean by modular here. And I'll write down some examples of this duality, and the talk is essentially going to be about two of these examples and how they show some evidence of some very deep relations between modularity and many interesting objects in algebraic geometry, such as motives and cohomology theories. Okay, so the examples are, the first one, the most basic one, quasi-modular forms. So probably you have already seen quasi-modular forms in the last weeks. One example is G2. So here, this is defined for every k bigger or equal than 1. So here, if you define them in this way, actually you need to impose that. Here it's fine to have k bigger or equal than 1. If you define it in this way, then this is not absolutely convergent for k equal 1, so you need to explain what you mean by that summation. But I really want to define them as this Q series. And G2, as you all probably know, is not quite modular, but it's quasi-modular. So this means that when you apply a modular transformation, this will transform like a modular form of weight 2 plus some extra term which kind of spoils the modularity. And as you also probably know, you can correct this problem by adding something which is now non-holomorphic, which is the imaginary part of tau. So these objects are called almost holomorphic modular forms. And I will denote them in the same way as the modular forms, but with a little star. So G2 star is defined as G2 plus 1 over 8 pi imaginary part of tau. So you see now this is not holomorphic anymore, but it has nice modular transformation, because if you apply gamma, then you get precisely c tau plus d square G2 star. So this is transforming like a modular form of weight 2. The second example are Eichler integrals Well, Eichler integrals in general are a good example of this kind of objects, but today I want to maybe show you just Eichler integrals of Eisenstein series, and I will denote them by putting a tilde on top of the Eisenstein series. So this is the Eichler integral of G2K. And now I want to consider actually only the modular Eisenstein series. So why is this an object of this kind? Well, it's first of all, how is this defined? So this is defined as the 2k minus first primitive of G2k. So this is a function which satisfies this identity. Of course, it's not unique, but the one I want to consider, so Eichler integrals are not unique. They are defined up to some polynomial which is killed by this by taking 2k minus 1 derivatives. The one I want to consider today is just you must define at each integration what's the constant of integration and just set it equal to 0. So that's my Eichler integral today. And why are they objects of this kind? Because if you consider the modular transformation, G2k tilde gamma tau, this is C tau plus D to the 2 minus 2k, G tilde 2k. But then you have an extra term, which I denote P gamma of tau, which will depend on gamma. So this is some polynomial. P gamma belongs to C of tau less or equal than 2k minus 2. So it's a polynomial of degree at most 2k minus 2. It's called the period polynomial of the Eisenstein series. It's a very interesting object. It's related with deep arithmetic properties of modular forms, the Eichler-Shimura theory. And in fact, for this normalization, the coefficient possibly up to powers of sure. And there is some non-holomorphic analog of Eichler integrals, which are modular. And this you have already seen in yesterday's talk. So these are non-holomorphic Eisenstein series evaluated at some integer k. Why? Okay, so non-holomorphic Eisenstein series are defined as follows. So this is im tau over pi. So you've already seen yesterday the definition, but let me repeat it. Sorry, here is the absolute value to the 2k. And they satisfy, I mean, they're modular invariant. I'm running out of space on this blackboard, so let me. Ek gamma tau is equal to Ek of tau. And they are non-holomorphic, obviously, because you have this absolute value and the imaginary part of tau. And why are they single valued? Sorry, why are they modular analogs of these Eichler integrals? I'll just give you an example. So you can write E2 tau as some coefficient which I didn't compute. G tilde plus G4 tilde conjugate plus some coefficient times G4 tilde prime plus G4 tilde prime conjugate plus zeta 3 over pi imaginary part of tau. So you see now you're doing something a little bit more complicated than here to make it modular. So you're adding something which depends on imaginary part of tau. The coefficient is now more interesting because it's zeta 3 instead of a rational. And you're not just leaving your Eichler integral, but you're putting its complex conjugate and something else, but which is essentially of the same kind. It's k 2k minus first primitive, and also you can write it as integral from tau to I infinity of tau minus z to the 2k minus 2 times g 2k of z dz, if you want, if you prefer. But if you write it this way, you need to regularize at I infinity because it's the Eisenstein series. So this is not convergent. Usually, for a cusp form, you can just simply define it this way. And it coincides with the 2k minus first primitive if it's a cusp form with 2k. Okay, so let me go on with this. Okay, so these are the only two examples I'm actually showing. Then let me just write a list of other objects because there's plenty. Well, okay, so this is kind of the simplest possible instance of a harmonic mass form. And of course, this is some non-holomorphic modular object, and on the other side, you will have mock modular forms. I'm not going to talk today about this kind of objects, but another generalization of this last example on this side amounts to talking about, so you can do iterated integrals of that kind, so you call these iterated Eichler integrals. So these were considered by Manin and Francis Brown. And they are very much related with yesterday's talk and with L series of modular forms and those sorts of interesting mathematics, but I don't have time to talk much about this. Very much related with this are elliptic multipositor values also, if you know what they are. And also something which I will talk about later, which are called holomorphic graph functions. So these were introduced by Johannes Brödel, Oliver Schlotterer, and myself a few years ago in the study of open string amplitudes, and they are the analog of what American was talking yesterday in the open string case. And on the non-holomorphic modular side, you will have, well, something which is called equivariant iterated Eichler integrals, equivariant, and then the same thing which is in there. So these were defined by Francis Brown. And they're also very much related with yesterday's talk. Then there are modular graph functions, which you've heard about. Which are modular non-holomorphic analogs of these holomorphic graph functions. So they were introduced. I think it's fair to give them to Green, Russo, Van Hove. They were the first who studied them systematically in 2008, and then many, many papers appear on this subject. But this is now the perfect starting point to go into physics, because their motivation comes from string theory, from physics. And so let me just be a little bit even more vague now. So here you have on this side open string amplitudes. And if you want, you have on this side gauge theories. And on this side, you have closed string amplitudes. And gravity. And relations, therefore, between this kind of objects and this kind of objects tell you something also about physics. In particular, double copy relations between gravity and gauge theory can be explained, as we will see, by understanding this kind of duality. Okay, but then if you know a little bit about these two words, then you know that on this side you have multi-valued objects. On this side you have single-valued objects. So I started from holomorphic non-modular, arrived to multi-valued, and here modular non-holomorphic corresponds to single-valued. So that's kind of the spirit of the talk, to understand this kind of duality in terms of single-valuedness or multi-valuedness of functions. And let me give a very last and easiest example, which is consider now logarithm of q. So the logarithm of q is, of course, it's a multi-valued function of q, for q complex number. So this is sent if you consider the this path, and you follow this path from one point to the same point. This is sent to logarithm of q plus 2 pi I. It's a multi-valued function. And you can see q as e to the 2 pi I tau. That's what we want to think of this talk. So this is 2 pi I tau. This is sent to 2 pi I tau plus 2 pi I. And this is just the t transformation as L to Z. So this is t, which sends tau to tau plus 1. So this monodromy kind of corresponds to the fact that this doesn't behave very nicely with respect to this element of SL to Z. And in general, you can take tau. I'm running out of space here, but you can take tau. And this will go, if you act by gamma, to a tau. Oh, sorry, I just wrote it here. So this is what happens to tau if you act by gamma. But if now you consider a single-valued analog of that, what would that be? So you want to kill this monodromy. So you consider, since this monodromy is purely imaginary, you can consider the complex conjugate of the logarithm, which is just logarithm of absolute value q squared. And well, this is minus 4. Well, okay. So first of all, this, because of the fact that this is imaginary, this is sent to log of absolute value of q squared. So this is a single valued function. And also this is minus 4 pi imaginary part of tau. And this is the kind of object that we've seen all the time on this side of the blackboard. So this is not surprising that it comes as a single valued object. And indeed, with respect to this transformation, tau going to tau plus 1, this is single valued because the imaginary part of tau is not touched by this operation. And so let me write here, if you act by gamma on imaginary part of tau, this is a much nicer modular behavior because this is imaginary part of tau over c tau plus d square. Good. Okay, so this was the introduction. Now I want to talk a little bit about quasi-modular forms and holomorphic graph functions, and then conclude by telling you something about single-valued periods and how they explain this kind of phenomenon. Is there any question? Okay, so now quasi-modular form and almost holomorphic modular forms are the simplest instance of this kind of correspondence. So I want to tell you something about these classes of functions. Hopefully it's not too boring for the experts. So quasi-modular forms can be defined, for instance, as the ring generated over Q by G2, G4, and G6. So these are honest modular forms. This is quasi-modular. We have seen it there. And then this is isomorphic to the ring of so-called almost holomorphic modular forms, for which the notation will be Qm star, which is just defined as Q of G2 star, G4, G6. And this isomorphism is just you send G2 to G2 star. So in particular, if you have an element in there, F in QM, then this F is some sum for J from 0 to, well, to something. Let me call it, well, let me call it K over 2, and this is the weight of the modular form. Cj G2 of tau to the J, Gj of tau, where Gj is a modular form, so it's in Q of G4, G6. So this is a proper modular form, and then you will have some powers of G2. This is how a quasi-modular form will look like. And this map will send this object into what I will call F tau star, which is the sum of Cj G2 of tau to the J, G2 star tau to the J, and then the same Gj of tau. Now, the first remark about this map is the following. So if you consider this weird-looking transformation, well, not weird-looking maybe, but so K is the weight of this quasi-modular form. Now you consider tau to the minus K F of minus 1 over tau. This is equal, because you know the modular behavior of G2 of tau and the modular behavior of Gj. This is an easy exercise. It's the sum of Cj G2 of tau minus 1 over 4 pi I tau to the J times Gj of tau. Okay, and now remember that G star of tau is equal to G2 of tau plus 1 over 8 pi im tau. So there is a very simple way, if you apply this strange operation, to go from this expansion to this expansion. You just formally send, you just formally send tau, which is log, so you just send 4 pi I tau, which is 2 log q. Okay, so let's say you send log q into log q square. So this is a strange looking thing to do, but that's essentially telling you that you can, term by term in this expansion, apply this kind of single valued operation, which kills the monodromy of the logarithm, and magically you find something which is a modular form. So this is the first remark. The second remark is that, so this is a remark by Li and Zhu. If you consider phi a function of many variables, so this will be a meromorphic function of variables living on the torus, E tau, which is C over Z plus tau Z, which is modular of some weight, which means that it transforms in the following way. So if you have these assumptions, then you can define a function f tau as the integral over 0, 1 to the n of phi dz1 dzn. you need to actually specify what you mean by this operation. It's not a priori well defined because of the poles of this function, but you can make sense of this, and this will be a function of tau. You're integrating over the other variables, and the first result is that this is a quasi-modular form. And also, if you define f of tau star to be, and then you can consider f tau star, because this is an operation you can do on all quasi-modular forms, and they have this formula for f tau star, which is the integral over the whole elliptic curve to the n, and also here you need to regularize this integral in some way, of phi, and now you need to integrate over the whole elliptic curve, so it's d square z1 d square zn over imaginary part of tau to the n. So this is a standard measure on the elliptic curve. And why did I show you this? Well, because this will be something that we will find again in the next example. But also, since I told you about this strange operation over here, what does this strange operation amount to in here? It's tau to the minus k f of minus 1 over tau. So this is the A cycle, if you want, of the elliptic curve. Well, this operation amounts to integrating over the B cycle of the elliptic curve. Okay, so these are non-standard facts about quasi-modular forms, so you may have not seen them, but they're very much related with the modular graph function story, so I think it's cute to present them. The index for, it's a Jacobi form, you mean? I believe they did consider some quite general objects. Yeah, I'm not sure. So there is a series of papers by these people and also many others, Ruan, and so they were interested. So the motivation was some problems in enumerative geometry. They wanted to show that certain generating series of in enumerative geometry are quasi-modular forms. This is some problem. That's actually why quasi-modular forms were born, to count ramified coverings of a torus, and then you have generalizations of this problem. I think with Gromov-Witten invariants of certain kinds, and so they built quite a general theory to study this kind of generating series, and they wrote nice papers. But I'm not an expert on it. The map? Oh, well, they, I think they, yeah, I'm not sure, I can't remember. I've studied the paper some time ago, but I don't remember. It must be something like that, yes. Yeah. Okay, so the next part, the next example is holomorphic graph functions. Oh, maybe I give you one little example here of this integral. So if you take phi as p of z tau, the Weierstrass p function, then it's a nice exercise to show that, well, I mean, this is very well known. The integral of the A cycle of p is just G2, which is a quasi-modular form. But it's not very well known that with the correct regularization, which is the most obvious you would think of, the integral over the whole elliptic curve of p d square z over im tau will give you G2 star. Okay, so let me first recall something about modular graph functions, which were already presented yesterday by Merrigan. So I want to define them in a different way, actually, so you can forget their definition from yesterday. So I want to consider the function g of z tau defined as minus log of theta z theta 1 z tau over eta tau square plus 2 pi im z square over im tau. So this is giving you the Green's function on the torus. Whoop. And let also gamma be a graph, so a connected graph with vertices, with n vertices v1, vn, and Lij edges between vi and vj. Then you can define modular graph functions associated to a graph gamma and depending on tau as the following integrals. So these are integrals over the torus to the n, powers 1 less or equal than I less than j less or equal than n of g of zi minus zj tau to the Lij times d square z1 d square zn over im tau to the n. So, well, I mean, you can see why I wanted to write almost holomorphic modular form in that way, because this is quite similar. And they are called modular graph functions because they are modular invariant. So you have d gamma of gamma tau equal to d gamma of tau. And an example which was already given yesterday is that if you take the graph with 2 vertices and 2 edges among them, then the modular graph function is just the integral over 2 copies of the torus of g of z1 minus z2 tau. And this is quite an easy exercise to show that you can rewrite this as a lattice sum. In fact, all of them can be rewritten as lattice sums, and that's the definition that Merrigan gave yesterday. But this one is a particularly simple one because it's on the nose equal to E2 of tau, the non-holomorphic Eisenstein series. So I wanted to give some motivation from physics for these functions. There was already quite a lot yesterday, but let me remind you that as Merrigan said yesterday, if you take the integrals over M11 of these modular graph functions, where are you? Don't you mean to integrate G square? Yes. No. Wait a second. No, I think it's fine to integrate G. So what you want to do is the exponential of no, I think it's correct this way. Oh, sorry. I thought in the general definition. Yeah. Here, you mean? Yeah, sorry. I thought here. Okay. Yeah. Absolutely. Yeah. You need a square because you have 2 edges here. Yeah. Okay. So as we've seen yesterday, if you integrate these kind of functions over the moduli space, which is not easy to do, and we have learned a lot yesterday about this, then this will give you coefficients of the alpha prime expansion of genus 1 closed string amplitudes. And let me just Okay, so maybe let me write a notation here, A1n closed. So these are functions of alpha prime, which is some parameter that when it goes to 0 gives you back the quantum field theory limit of string theory. So as soon as you compute higher order corrections in alpha prime, you are computing the string theory correction to the theory. And let me remind for those who don't know much about physics in the audience that what you want to do in string theory is compute some perturbative amplitude, which is given by a series for h bigger or equal than 0 of, well, this is a first approximation of what an amplitude looks like for a mathematician. So amplitude of n particles with closed strings, let's say, they depend then on some string coupling constant 2h minus 2. So computing these kind of integrals will give you the genus 1 contribution to this kind of perturbative expansion in GS, but then there is another expansion in alpha prime. So there are two expansions to do in string theory. Okay, so maybe a last fact about modular graph function is that, so this was first proven in my PhD thesis, and then, okay, so let me first give you the statement. So you can asymptotically expand at infinity holomorphic graph function as follows. So these are, well, not asymptotically, this is an exact expansion. So you have an expansion of this kind where absolute value of gamma is just the number of edges of the graph. And these numbers here, these coefficients of the expansion, are multiple zeta values. So the fact that they're multiple zeta values was proven by Eric Panzer, improving a result of my thesis. And now I want actually to focus on the very first, the contributions to this expansion, which is those which are not suppressed exponentially. So this is sum for k from minus gamma to gamma of dk 0, 0 times minus 4 pi im tau to the k plus big O of q. And this part, this is a Laurent polynomial, I will call it little d gamma of tau. Number of edges. Edges, sorry. Okay. Sorry? No, well, so you can write formulas, but not completely not in complete generality, but for certain classes of graphs, you can write explicit formulas in terms of very complicated numbers, which are not clearly multiple zeta values if you just look at them. Then if you do some clever reductions, you can reduce them to multiple zeta values. So it's already very difficult to prove that they're multiple zeta values, and the proof is not constructive. And in fact, it is conjectured that they're lying in a very small subset of multiple zeta values, which are introduced very soon. So these are difficult numbers to compute. Okay, now let me tell you something about holomorphic graph functions. So this is, so let me first define A gamma of tau. So there will be two families, A holomorphic and B holomorphic graph functions. A holomorphic are just defined as the integrals over 0, 1 to the n of the product of, well, here I want to consider a half of g of zi minus zj tau to the Lij. And actually, you want to define this by restricting to tau equal it for t real, and then you will analytically continue. But in order for this to be well defined, you need to restrict tau first. And then dz1, dzn. So again, here, this is very much looking like those integrals considered by Lee and Zhou. Yeah. So this is the a slight modification of the open string propagator. Here you can show that if you restrict this to tau equal it and zi zj living in 0, 1, then this coincides essentially with the open string propagator up to a constant. And this constant is crucial because it makes the integral of the single Green's function equals 0 on 0, 1, which is not the case for the usual open string propagator. And that is what you need to define nice analogs of the modular graph functions, because that's a property that the modular graph functions have. Yeah. Okay, so this is what we want to define. This is very much related with open string amplitudes, but not quite. It's some object inspired by open string amplitudes, and combinations of these objects actually compute coefficients of open string amplitudes. And then you can define the B gamma of tau as A gamma minus 1 over tau. And again, like here, you can show that this is equal to the integral, where 0 tau to the nth over the B cycle of, well, the same thing as here. But then the measure is going to be dz1, dzn over tau to the n. And so as I said, these are related with the computation of open string amplitudes in genus 1. And now a fact, which I proved a few years ago, is that they also have an asymptotic expansion very similar to the ones of modular graph functions. Now sum m bigger or equal than 0, b k m, and then 2 pi I tau to the k q to the m. And also, again, here I want to mostly focus on the very first contribution, so the one which is bigger at infinity. So this is sum for k of bk0, 2 pi I tau to the k plus big O of q. And this part here, I want to call it b gamma tau. So this is the analog of d gamma tau over there. Okay. Now, the remark, and I'm going to be really vague here, is that d gamma, so this was made in the paper where the holomorphic graph functions were defined, which is a paper I wrote with Johannes and Oliver a few years ago, that these functions, they all satisfy, and here let me be very vague, very similar algebraic and differential relations. And also, if you look at the constant terms, or let's say the big term in the asymptotic expansion, b gamma and d gamma, they're also very similar. And let me just give an example to make you understand a little bit more what I mean by very similar, and then later, hopefully, I can be more precise about this. So b of tau with respect to the graph with 2 vertices and 2 edges is just equal to 2 pi I tau square over 720 plus zeta 2 over 3 minus 2 zeta 3 over 2 pi I tau plus, no, sorry, minus 6 zeta 4 over 2 pi I tau square. Whereas D, associated to the same graph, is equal to 2 pi I, sorry, minus 4 pi im tau square over 720, then minus 4 zeta 3 over minus 4 pi im tau. So, well, okay, it seems a bit random to say that they're very similar. They are quite similar, but we will see later that there is some deep meaning of the term very similar about these two polynomials. You can just go from here to here by killing this term, multiplying this term by 2, and transforming 2 pi I tau into minus 4 pi im tau. Okay. Now the last part of the talk is about single-valued periods and how they're related with modularity. So this is a little mathematical parenthesis of the talk. So the theory of single-valued periods was introduced by Francis Brown in 2013, motivated by this kind of modular graph functions, so by string theory amplitude computations. So, okay, so a little bit of mathematics. So now let X be an algebraic variety over the rationals. Then you know that there is the, well, for a manifold, you know that there is the de Rham theorem that gives you an isomorphism between the de Rham and the singular cohomology of a manifold. There is an analog in the algebraic case, which was proven by Grothendieck. So you have algebraic de Rham cohomology groups of X. You tensor this with C, and this is isomorphic to the singular cohomology of the complex points of X with rational coefficient tensored with C. And this goes exactly in the same way, well, at least in the simplest cases, this goes exactly in the same way that goes in the smooth case. So you have a differential form here, and you just associate to this the function which takes a cycle and you integrates the differential form over that cycle. And this is a complex number. And these numbers are called periods. So you can now fix a basis of your cohomology groups, both de Rham and singular, and then this isomorphism, it's an isomorphism of vector spaces, so it is represented by a matrix, and this matrix is called P, sorry, is denoted P and is called the period matrix of the isomorphism. So the entries are going to be periods given by integrals of whatever basis you have chosen for H de Rham over over cycles, over your basis of cycles in the singular cohomology. And now suppose that your variety X is depending on a parameter. So let's say you have a family xt for t living in some base space S. So this is let's say it depends algebraically on the parameters, an algebraic family of algebraic varieties. But then now the differential forms will depend in general also on this parameter. And so this period matrix also will depend on the parameter t. Sorry? S is the space where t belongs to. Sorry. So t belongs to S. This is some space. It's a parameter. So now this is a family of algebraic varieties which depends on some parameter t which lives in some space S. Yeah. In some parameter. Yeah, yeah. And on the algebraic, because this is some algebraic story about periods. So, well, if you now compute the period matrix, it turns out that periods are, well, because all of this is algebraic, then it turns out that periods are holomorphic functions, well, possibly meromorphic, depending on how you define this isomorphism. But let me just write holomorphic functions of t and satisfy as functions of t, very famous kind of differential equation, which is called Picker-Fuchs equation. Picker differential equation. And but holomorphic solutions of differential equations of Picker-Fuchs type, since this has in general regular, well, it has to have regular singular points. It means that if your base space S is not simply connected, if S is not simply connected, then the periods will be also multi-valued functions. They will be analytic continuation of the local solutions of these Picker-Fuchs equations along paths which will in general encircle singularities of S. Okay, so I'm a bit late, but still let me give you a little example maybe. Okay, so an example is log t. So log t is a period function because it's a function, it's an integral from 1 to t of dz over z, and you can show that this can come from that algebraic machinery. I don't want to do it now, but and this function is precisely the kind of function I'm talking about here because it's holomorphic. And it's a solution of a Picker-Fuchs equation, which in this case is just d over dt f of t equal 1 over t. And it is, of course, multi-valued. So, well, you get from this Picker-Fuchs equation, actually, you get a monodromy representation induced by your period matrix. So, so you have some map induced by a fixed period matrix and satisfying a certain differential equation. You get a map from pi 1 of S to GL some GLK of Z. And the fact that the entries are integers of the monodromy is a special feature of Picker-Fuchs equation. So this is ensured by the fact that they're period matrices. Essentially, it's ensured by the fact that they're coming from singular cohomology. And okay, so let me say that an element gamma in here goes to big M of gamma. So what happens to the period matrix if you act by monodromy along one of these cycles? Your matrix gamma, P of tau, is going to be sent to M gamma times P of t. So this is the monodromy along gamma. And how can you cure this multi-valuedness? So how can you replace P by some object, which is now going to be single valued with respect to this kind of monodromy operators. There is an obvious answer because M of gamma has integer coefficients, so in particular real coefficients. You can consider this kind of ad hoc definition, which is P T single valued, which I define as P minus 1 of T conjugate times P of T. Well, now if you apply the monodromy along a cycle gamma to this matrix, you are going to get P T minus 1 conjugate M gamma minus 1 conjugate M gamma P of T. But this is real, so this is going to go away, and you get again the same matrix. So this is now single valued on the base S. So this is a very naive looking operation, but there is some very deep algebraic geometry behind this operation. Now, let me give a brief example how this goes. So you have the logarithm of T is part of a period matrix which goes like this, 1 log T 0 2 pi I. So you have to believe me on this. And then the monodromy along the cycle which goes around the origin of this matrix is, well, 1 is just 1. Log T goes to log T plus 2 pi I. This goes to 0, this goes to 2 pi I. And this is equal to 1, 1, 0, 1 times the original period matrix. So this is the monodromy representation of this cycle, and it has indeed integer coefficients. But then if you now apply this prescription to this matrix, now this matrix is sent to, well, you do the computation, and it's just 1 log of absolute value of T squared, 0, minus 1. So you get again this log of absolute value of T squared, and here the interpretation is it's just a single valued analog of this log T out of this formalism. You can also show that it satisfies whatever you find out of this formalism satisfy exactly the same Picard-Fuchs equation, but it's now a real analytic solution of the Picard-Fuchs equation. So it is now not holomorphic anymore, but it's single valued. Sorry? Yeah, there is the determinant is 2 pi I, so you divide by, yeah. Okay, so I'm getting close to the end. Sorry, I'll be slightly over time if it's okay, maybe 5 minutes over time. Okay, one remark is that this construction makes sense also for constant period matrices. So you don't need your period matrix to be depending on a parameter T. But then what you're getting now, it's some single valued analog of like some number, which is kind of a single valued analog of the numbers in the original matrix P. So the entries of the matrix P single valued obtained in this way are called single valued periods. And the reason why they're called single valued periods, of course, comes from this motivation here, because as functions of a parameter, they will be single valued functions. But funny things then happen on the numbers. So you can actually define single valued analogs of numbers like zeta k. So zeta single valued of 2k turns out to be equal to 0. And zeta single valued analog of 2k plus 1 turns out to be equal to 2 zeta of 2k plus 1. But this is very nice, because now I want you to look again at this example. if you follow just that prescription, plus sending 2 pi I tau to -4 imaginary part of tau, but this is also part of the single valued prescription because it's what we did with that log t square, then you can go from B to D. And that's a general thing. So this is now, I will conclude with a list of observations and questions. So conclusion. So the first one is a very trivial observation. It's in fact just the definition if you want. Well, not the definition, but it's something very well known. So M11 is the orbifold quotient of H by SL2Z. And there is a notion of, so this is the moduli space of genus 1 Riemann surfaces with 1 mark point. And there is a notion of a fundamental group, orbifold fundamental group of an orbifold. And in this case, this is precisely SL2Z. What happens here is that this is, if you want, the universal cover, orbifold universal cover in a sense of this space. And this is the fundamental group. So if your parameter lives in this space, then something, a period matrix depending on a parameter which lives on this space will be non-modular if it's multi-valued with respect to this action of the fundamental group, or modular if it's single-valued with respect to the action of the fundamental group. So that's now a slightly more precise meaning of what I mean by modular versus monodromy. So another thing I want to mention is that, okay, so as I already said this, so there is this conjecture, B gamma of tau sent to D gamma of tau by this very simple operation log Q sent to log absolute value of Q squared. And also you want to send multiple zeta value zeta of K to single valued multiple zeta value zeta of K. So you can define these in general. And this means that the coefficients of the modular graph functions are very special kinds of multiple zeta values, which are called single valued multiple zeta values. So this was already noticed in my thesis before this conjecture. So it's a kind of a stronger version of the conjecture that the coefficients of these are single valued multiple zeta values. So they also come from something which arises in open string amplitudes. And maybe one last comment. Okay, so two last comments, if I may. So one comment is that you can write the single-valued analog of a period. This was proven by Brown and Dupont as an integral over the whole variety, the complex points, of the same differential form wedge, some kind of dual of your cycle of integration. And this very much looks like this kind of integral representations of quasi-modular, almost holomorphic modular forms, modular graph functions, and holomorphic graph functions. And then because this is given also by this kind of operation on the period matrices, then you will have a factorization of this kind of integrals as linear combination of products of these guys and their complex conjugates. And this will give stuff which look like Riemann, well, in simplest cases, these are Riemann bilinear relations. And in physics, there are KLT relations in string theory between closed and open string amplitudes. Or in conformal field theory, you get conformal block decompositions. And in general, you get double copy relations between gauge theories and gravity. And the very last comment is that to go back to quasi-modular forms, if x now is an elliptic curve, then the period matrix is omega 2, omega 1, eta 2, eta 1. Sorry for putting the 2 upstairs, but there is a reason. So these are the periods of the elliptic curve, and these are the quasi-periods of the elliptic curve. And now if you compute the monodromy with respect to, so this will depend on which basis of cycles you have chosen to define your torus. And if you change that, it amounts of acting by SL to Z on the period matrix. And the monodromy is precisely given by by precisely gamma, the period matrix, times, by precisely gamma, the element of SL to Z, times the period matrix. And the remark, to go back to quasi-modular forms, is that if it is well known that if tau is equal to omega 2 over omega 1, then P is equal to a matrix given by tau 1, G2 of tau, tau G2 of tau, minus 2 pi I, times omega 1, 0, 0, 1 over omega 1. So in particular, the fact that you get G2, the quasi-modular form over here, it's a relation very classical due to Fricke. And this means that this monodromy that acts on that is non-trivial for the period matrix of an elliptic curve is essentially equivalent to the fact that there is some lack of modularity for the G2 quasi-modular form. And now I want to do the computation because I'm already out of time, but if you just compute now the P single valued out of P, then one of the entries will be G2 star, which is the almost holomorphic one. So now this relates also in this example, holomorphicity, modularity, monodromy. Okay, so this is it. Thank you. No, I don't. It's very, yeah, so it's completely clear what happens in the quasi-modular forms. You just have rational coefficients, so you map rational coefficients to rational coefficients in the almost holomorphic. When you start having periods and Q bar expansions, things get much more complicated, and the conjecture, well, I think part of this conjecture is now proven, but Francis Brown has built, using the theory of single-valued periods, some closed string analog of iterated Eichler integrals, where you know exactly what happens to the whole expansion, and there is no simple prescription like you send one term to the other with this very simple operation, as far as I know. Not even in the Eisenstein series case, in the non-homomorphic Eisenstein series case. But there is a conjectural prescription which is very complicated to go from the whole function to the other whole function. But as far as I know, not looking at the single coefficients of the Fourier expansion. Yeah, exactly. Exactly. So there are results on this by Axel and collaborators. There are many nice papers. I kind of lost track of the latest results, but I think you have now proven that that up to constants, the generating series of modular graph functions should coincide with the one of Francis Brown, as far as I understand. So the only thing remaining to prove to relate modular graph functions with this formalism is that essentially that these Laurent polynomial have single-valued multiple zeta values as coefficients. That's the last conjectural statement. Yeah. Mhm. Yeah. It's in the direction of this observation. So now, so here I didn't write down the example, but so quasi-modular forms appear in period matrices in this way, and then in more complicated ways, the more general ones. And almost holomorphic appear in the single-valued period matrices. But elements of single-valued period matrices can be written as surface integrals, or like integrals over the whole variety. So I guess, I mean, I don't know it for sure, but I guess there should be some, you should be able, if you take X to be some configuration space of points on Riemann surfaces, to view those integrals as periods of this kind. No, I don't think it's been related with the Francis theory of single-valued periods. No, it's. I found this relatively recently in these papers, and I thought it was a cute thing to present today. This quasi-modular versus modular graph function. Yeah. So I wanted to underline that because I also noticed it was very similar, but I don't think there's any work on that for the moment. Sorry? Yeah, so the single-valued period formalism, you need to be very careful if your number field is not contained in R. So elements of the period matrix, as soon as your field of the algebraic variety is contained in R, will be real numbers, because all this is essentially induced by complex conjugation on the complex points of the variety. But you need to be a bit careful if your algebraic number field is not containing the reals. It is explained in a nice paper by Brown and Dupont. There is a remark on what to do in that case, in the most general number field case. You're still going to get periods, because a period can be defined in the same way, but over Q bar, and still you will get periods, and you also have a theory of single-valued periods for them. The monodromy is still going to be, so it's still Picard-Fuchs differential equations. The whole theory of periods goes through. So the monodromy is still going to be, as far as I know, with integer coefficients. Yeah. Sorry? No, I think it should be still integers. I mean, I'll think about it, but I think Picard-Fuchs equations are very special. What can happen is that you can find a period as an element of a smaller period matrix, and for that smaller period matrix, the monodromy matrix will be with coefficients in some extension of Q. But I think there will always exist a motive whose period matrix contain the period you're interested in, and whose monodromy will have integer coefficients. That's the statement. I'm not saying that because a period can be seen, I mean, a single period can be seen as an element of many different period matrices. So my statement is there will be some period matrix such that your period will behave with a monodromy in Z. If you have? Yeah. So you need some assumptions. You need a smooth projective variety, but then you can also do this whole story with the relative cohomology. So you can have some divisors, but then you will need these divisors to be normal crossing. So there is some technical assumptions. I completely skipped technicalities.